Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, welcome back to Physics with Beth and Beth. I'm Beth, and today we are continuing our talk on AP Physics 1 Unit 5, which is on torque and rotational dynamics. And so in this video, we're going to be doing a couple practice problems related to balancing torques. So let's get started. This is the little problem we've got here. We have what is called a flywheel. Now, if you are like me, you might not know what that is. I had to have my fellow Beth explain it to me. A flywheel is just a thing in machines. It's a metal disc. You've got belts or cords attached to it, and then in the center we have another smaller disc that is welded to it and fixed. So I have two circles drawn here, but they are stuck together and will rotate with the same angular velocity. It's just two circles glued together is all we've got here. But we're going to call it a flywheel so that we sound like we know what we're talking about. Okay, so I have my larger circle with a radius of 0.5 meters and my smaller circle with a radius of 0.25 meters. And I have a few different forces pulling up and down on my flywheel here. And so what we're going to try and find is the net torque acting on my flywheel here. So really all we're going to be concerned with is the left side of Newton's second law of motion for rotational dynamics. Yes, if we find the net torque, then that is going to be equal to the angular acceleration times the moment of inertia. But all we're going to worry about right now is finding that net torque. So our net torque is literally just the sum of our torques, right? And of course we have to remember that whenever we calculate torque, any torque that we calculate is just going to be equal to the radius of that torque. And remember, this radius is not necessarily the radius of the circle, but it is the distance between our axis of rotation and the point at which our torque is being applied. So R stands for radius, but not as in radius of a circle, as in distance between axis of rotation where a torque is being applied, times the perpendicular component of whatever force is going to be causing our torque. Okay, so before we get into actually calculating these values, let's figure out which direction each of our forces are pulling our circle in. Now, we could just look at this circle and say, hey, I've got two forces pulling down and one pulling up, done. But because these forces are going to be causing rotating things to happen, we need to figure out which direction they're going to cause our wheel to rotate in. Now remember, whenever we talk about rotation, we have a positive and negative direction, where counterclockwise is positive and clockwise is negative. And I know that feels a little counterintuitive, but there are a lot of reasons that go behind that you'll get into as you get into higher level physics classes. But for now, we just got to accept counterclockwise is positive and clockwise is negative. So we have force 1 here that is on our, for you guys, that's the right side, and it is pulling downward like so. So that is going to be causing a clockwise rotation to be happening. So force 1 is going to be pulling clockwise. So I'm going to make a little note here that force 1 is negative. It's going to be causing a negative torque. Force 2 is on the same side of our circle, but it is pulling upwards. So, as you might guess, it is going to cause a counterclockwise rotation, like so. So that would be a positive torque associated with force 2, and then force 3, I'm gonna just set my cap of my marker aside here. Force 3 is on the left side for y'all, I believe, pulling downward. So that is also going to be causing a counterclockwise rotation. So this one is positive. Now, if we didn't know how to calculate torque, we might be tempted to say, hey, look, I have 30 plus 20 newtons pulling in a clockwise direction, and I have 50 newtons pulling in a wait, let me flip that. I have 30 plus 20 newtons pulling in a positive or counterclockwise direction. So 50 newtons total pulling counterclockwise. And then I have one force of 50 newtons pulling clockwise. 50 in one direction, 50 in the other. I'm going to have a net torque equal to 0. Done. But because we know how to calculate torque, we know that that's not true. We know that we have not just the perpendicular component of force to worry about, but also the radius at which those forces are acting upon our flywheel. So if we actually get to calculating our net torque here, we see that not everything is going to be 0. But I'm going to stop giving y'all spoilers and let's actually get into calculating this problem. So we have our net torque that's equal to the sum of our different torques, where torque is equal to radius times the perpendicular component of force. So torque 1 here is going to be the radius that force 1 is acting on, which is at the radius of our bigger circle. So that's radius 2, so 0.5. So this is going to be 0.5 meters times the perpendicular component of force 1. Thankfully, the perpendicular component of force 1 is just force 1 because it is already perpendicular to our axis of rotation here. So that is just going to be 50 newtons. And then, because this is pulling clockwise, we know that this is going to be a negative torque, right? So we're going to pick up a negative sign at the beginning. And so that is our torque 1 here. Then we're going to do torque 2, all right? So torque 2 is being caused by force 2. Force 2 is acting at a distance of our first radius away. It's acting on our smaller circle. So it's acting at a radius of 0.25 meters. And the perpendicular component of force 2 is thankfully just all of force 2. So that's just 20 newtons. And because it is pulling in a counterclockwise direction, we don't pick up a negative sign. That is exerting a positive torque here. And then we have force 3. I'm going to have to go on to another line here. Force 3 is acting on the radius of our larger circle, the larger part of our flywheel here. So that's acting with radius 2, so that's the 0.5 meters again that we get. Oh, and this is meters. And then it has a magnitude of 30 newtons, being the perpendicular component of our force there. So this here is torque 1, this is torque 2, and this is torque 3. So we're just calculating the sum of our torques by adding all of our torques up together. We've got them all calculated there, and now we can just plug this into our calculator. We'll end up finding that our negative torque here ends up being just negative 25 Newton meters. And then we have plus, let's see, 5 Newton meters plus 15 Newton meters whenever we multiply these things out. And whenever we add all of those things together, we end up finding that our net torque on our little flywheel here is actually equal to negative 5.0 Newton meters, which means we're going to have a net rotation of a clockwise rotation. Goodness gracious. We have a net torque that is pulling in the negative direction. So even though we have equal magnitudes of force pulling in both counterclockwise and clockwise directions, because those forces are acting on our flywheel at different radiuses, they have different net torques that they're exerting on our system, our little flywheel here. So that is our first little practice problem there, and we have made it all through. Great job, guys. Let's go on to the next one. So our second little practice problem here that we're going to work through is two children sitting on a little teeter-totter. And we're going to try and figure out exactly what masses are needed to balance it. So this is our little system here. We have a little teeter-totter with a little support here. And we have one child sitting on one end of the teeter-totter. We're going to pretend this is beautiful art. And he is 0.5 meters from the little support. So he's pretty close to the balance here. And we have another kid that is sitting 1 meter. So this is child number 2. And child number 1, this kid over here, this is the big brother. He has a mass of 65 kilograms. He's a pretty big kid. This is like an 8th grader or something. And over here, we are trying to solve how large of a kid we need over on this side in order for our system to be perfectly balanced, to be in equilibrium. So we don't know this kid's mass, but we do know this kid's mass. So whenever I say we want our system to be balanced, we want it to be in equilibrium, I don't want any rotation happening, that should cue you in, oh, okay, so I don't want any rotational acceleration. I want that to be 0. So that means that I want my net torque, which is equal to my angular acceleration times my moment of inertia. Well, if this is 0, 0 times anything is 0, I need my net torque to be equal to 0 in this system. So I need the torque exerted by child 1 to be the same as the torque exerted by child 2. So what is the torque exerted by both child 1 and child 2? Well, the torque exerted by child 1, first of all, let's draw a little arrow here. It is pulling down on this side of the system. So that is causing, wait, which direction is that? That is counterclockwise. Okay, and this child, so this is counterclockwise. This child is exerting a counterclockwise torque. And this kid over here, his weight is pushing down on this side of the system. That is causing a clockwise rotation. So I'm just going to make a little note over there. So my net torque is going to be the torque of child 1 plus my torque of child 2. And I know that my torque of child 1 is going counterclockwise, so that's going to be positive. And I know my torque of child 2 is going clockwise, which is going to be negative. So remember those signs whenever you're talking about rotation. So I know that the torque exerted by child 1 is going to be equal to the radius, his distance from the axis of rotation, which is the little support of my teeter-totter here, times the force that he is exerting pushing down on the teeter-totter. So that is going to be the force of gravity on child 1. That is what he is using to push down on the teeter-totter, right? It's just his weight. Okay, and then I know the same thing here is going to be true for force for child 2, except I'm going to pick up a negative sign because this is going to be exerting a clockwise torque, right? So it's going to be torque 1 minus torque 2. My first radius is 0.5. The force of gravity on my first child is just going to be 65 kilograms times the acceleration of gravity, which I'm just going to leave as a little g here, minus, here we go, minus my second radius, which is 1 meter, times the force of gravity being exerted on child 2. I'm going to leave my m out because that will be confusing with my symbols here, which is going to be the mass of child 2 times the force of gravity, or acceleration of gravity, which I will also leave as a g. Okay, and now we know that we need all of this to equal 0 because we're trying to find a system that's in rotational equilibrium, right? So this is going to be 0 is equal to 0.5 times 65g minus 1.0 times m2 times g. I'm going to bring this over to the right side by adding it to both sides of my equation. I'm going to find that 1.0 times m2 times g is equal to 0.5 times 65 times g. Okay, and now, because I left my g's out, they are just going to cancel out. But I don't want you guys to get lazy whenever you're doing problems like this. Just because our g's canceled out in this instance doesn't mean that they're always going to, depending on exactly what forces are causing the torques. Depending on what forces are causing the torques on each of the different parts of your system. So while for us our g's did end up canceling out, we can just simply cross these out, divide that out on both sides. That's not always going to be true. So just write the g. If it ends up canceling out, great, you had to write exactly one extra letter. And if it doesn't end up canceling out, you're going to be glad you wrote it. So that's one little caveat that we see students make that error quite often. So just keep that in mind. Don't stop writing the g because you think it's going to cancel out, because it won't always do so. And also your units will be wrong if you leave that out. Okay, so here we go. We end up finding that 1 times m2 is equal to 0.5 times 65. If I end up solving this out for m2, we end up finding that the mass of child 2 is equal to 32.5 kilograms. And there we go. The mass of this little kid sitting a meter away from our support in order to keep our system in equilibrium is 32.5 kilograms. Now, there are just two quick little concepts I want to talk about in relation to this. Our system is in perfect rotational equilibrium. It's not rotating in either direction, even though we have different masses on either side of our little support here, on either side of our axis of rotation. This is a concept question you might end up seeing on an AP Physics 1 exam. Something along the lines of, hey, if I need a system to be in rotational equilibrium, do the masses on either side of my axis of rotation need to be the same? Well, no, they don't. We just saw here, we have two kids of two very different masses. This kid's 65 kilograms, this kid's 32.5 kilograms. But because they are sitting at different radiuses, different radii, from our axis of rotation, which is right here at our support, they end up exerting different torques, or they end up exerting the same torque even though they have different masses. So you don't need the masses on either side of your axis of rotation to be the same. The other side of this, the other concept question you might end up seeing on an AP Physics exam is something along the lines of, well, do I need my masses on either side of my axis of rotation to be operating at equal radiuses from that axis of rotation in order to have a system in rotational equilibrium? And again, the answer is no. We have a perfect example here where we have two masses of different magnitudes operating at different radiuses away from the axis of rotation, and yet we have a system in perfect rotational equilibrium. So that was two examples summing up torques and finding the net torque on a system. Thank you so much for sticking with me through all that, guys. If you have any questions, comments, if you liked it or hated it, please let us know in the comments. They'll try and be nice. Beth and I read all of the comments, so if there was something that wasn't quite positive, anyway, I'm gonna stop talking. Thank you so much for sticking with me through all of this. I hope you all have a lovely day and happy physicsing.